We're going to cover the final two parts of our chapter 11. Right, so let me just orient ourselves. Okay. Okay, so you can see network virtualization and network automation is part 3 and part 4 of our chapter 11 lecture. So this afternoon, we're going to look at virtualization and automation. Yeah. Now, all these two, all right, are under emerging trends in networking. You start to see them more and more in the future because some of the technologies that use virtualization and automation here is we start to see. Kelvin is in school. Oh, didn't let me know. So, Kelvin, where are you receiving this lecture? If I, oh, you're at the library. If I knew, we could have gone to the lab, but it's okay. We continue online first, yeah. Maybe tomorrow, you guys maybe want to be at the lab. All right. So, okay. So we continue. Yes, Kelvin. Did you find out where is the exam hall? So, oh, okay. So it's um, above the how is it that the canteen there, right? Last time the graduation. I will have to check whether I have the map, right? I will have to check this. But you know the canteen? Yeah, above the canteen, right? Above the canteen, there's examination hall. All right. Okay. Anyway, so we're going to start on virtualization and automation. As I mentioned before, these are emerging trends because of the technology that they support, like cloud computing, right? Is one of them. Um, Cloud computing brings with it virtualization. Okay, so definitely when we can virtualize our infrastructure or infrastructure as a service, yeah, IaaS, right? Part of the cloud computing paradigm. Then network virtualization also included within it, right? So let's start. Okay, let me just start my recording. Farah will be joining us a bit later. Okay. Okay. So the topics we're going to cover under part 3 of chapter 11 is, as I mentioned before, cloud computing and virtualization, right, leading to virtual network infrastructure. And then we look at software-defined networking and finally controllers. Okay, this is for part 3 of chapter 11. All right. So let's have a look at cloud computing first. All right, so let's have a brief overview of what is cloud computing. Right, so we actually, in my opinion, we actually come full circle, right, for cloud computing. Earlier on, before the advent of personal computers, right, the only way you can get access to computing services is that if you have access to a terminal, and usually these terminals are dumb terminal. Okay, I'm talking about 1960s, 70s era of computing. And those dumb terminals usually are connected to a very powerful mainframe computers. Well, I say very powerful for those era, right? Very powerful. Nowadays, um, we have more powerful, smaller machines, more powerful than that. But one thing I have to say is that it's all centralized. Okay, these mainframes are put into a central location, right? Into a data center, right? There are no personal computers, therefore you access via dumb terminals, and that means you can't do any computation at the terminal. All computation will be done at the mainframe, right? And then comes the era, 80s and after that, came the era of personal computing, right? IBM personal computer was released, and it started off an industry. Okay, people are now having the freedom to have and to own, and having the affordability, right, of having their own personal computer. And due to this, there's another paradigm that comes in where computation is done at the edge. That means at the personal computer side, right? But we come full circle because after that, they start to talk about thin clients. Thin client basically is a workstation that is not that powerful, but enough for you to work some minor computation at the client side, but most of the computation is done at the data center, right? And it follows through right now, even with powerful desktop. We still can offload, yeah, the computing services that typically an enterprise will need to manage themselves. Last time, enterprise have to have their own data center, have to manage their own servers, and all this, right? But now there are services provided by companies, right, that allow you to have infrastructure, application, storage, and etc. at their data center. So enterprises do not need to manage this, maintain this, or even need to come up with the budget to create such a data center. Okay, so they pay for the service of having, right, all these data center services run by another company. Example, Amazon, right? So Amazon is providing something called cloud computing. So we back to the 1960s paradigm, right? So why does why suddenly cloud computing is so attractive? Is because, first of all, because it's on the cloud, the organizational data needs does not need to be restricted to a certain location. As long as you have access to the internet, you can have access to your cloud, yeah, to the cloud that stores all your company data, information, and so on, right? And in terms of budget, enterprises no longer need to maintain a budget that is serving their own data center. Have to hire IT personnel, have to do backup, have to maintain, manage, and scale up, right? So they've subscribed to cloud computing services, uh, um, just very lean, just enough to fulfill their data center needs. So you can see streamlines the organization IT operations, whereby they can subscribe to only the services that they need, right? So basically, can be very precise what they need. At any time, they can simply change, okay, what are their requirements, and the cloud computing services will provide to them and charge only those services that they actually use, right? So it eliminates or reduces the need for on-site IT equipment maintenance and management. That means enterprises now no longer need to worry about all this provision. It's done by the cloud computing provider. Okay. In the same vein, it reduced their costs for the enterprise because now they do not have the need to deal with data center equipment, energy. Energy here means the power needed, okay, to power those infrastructure, those servers, right? Not only for the physical equipment, but also the to maintain the environment. Okay, example, if you have servers, they generate a lot of heat, so you have to safeguard these servers, okay, so they don't get damaged. You have to provide a very cold environment for the servers to operate. So those take really a lot of energy. Okay, so if you if as an enterprise, if you subscribe to a cloud computing service, yeah, then you don't have to worry about all this. You don't need to worry about equipment, energy, physical plant requirements, personnel to manage that data center, because the cloud computing services handles all this for you. All right, right, and also it's very easy to scale up. Simply it elevate your requirement, elevate your needs, right? Okay, so maybe let's say in terms of storage, maybe you need 1 terabyte. Suddenly, because you now outgrow the 1 terabyte. Okay, now your data is generating more. So you simply elevate your subscription to the next level where it provides you extra storage space, for example. So it's very rapid. You simply there's a dashboard. You simply change your subscription. Of course, you have to pay more, but then you don't have to worry about, purchasing, going through all the tedium of purchasing, getting quotation, installation, all this thing, right? You simply go to the dashboard, say you need more storage, and you can precisely say how much more storage you need, then you can get it. That's how easy it is. It's very rapid, very fast, right? And for certain services, they call elastic. You can scale up or down depending on your day-to-day requirement, right? That's very flexible. So this is very attractive to enterprises. Sometimes the services are pay as you go, yeah, pay as you go. All right, but monthly basis lah, monthly basis. All right, so there are three provisions for cloud computing services, right? So and depending on what kind of service the enterprise is subscribed for, it may be one of these, or all three of these, or two of these. Okay, so depending on the needs of the enterprise. So the first one is software as a service, or SaaS. So for this software as a service, the cloud provider uh, will provide access to applications and services to that enterprise that subscribe to this. And all these are delivered via the internet or over the internet, right? So basically, the software as a service is the enterprise will access the cloud to run application and to get services, right? The second type is platform as a service. Now, platform goes a bit lower level. Software as a service is application, software application, right? Platform as a service is including development tools and usually the operating system. So not only you can choose what application you want to run, could be a server application, yeah, but the platform, the OS that the application runs on, right? And if you want to manage some of the develop tools or application yourself, then you can have access to development tools and services. As an example, you might have a small team, IT team, that will write some code, right? So the cloud services is able to integrate, okay, the uh, the testing and the upload, okay, of the application that's written at the client side, okay, to the cloud, right? So the workflow is very quick. Okay, so in this kind of environment, the cloud services offers platform as a service. Okay, the third one is a bit even low level, right? Because this is provision of infrastructure as a service, or IaaS. So in this, not only that the cloud provider provide you application and the platform, but also give you access to the infrastructure. So infrastructure here means you will get to access to network equipment, virtualized network services. Means virtualized network services means network services that is running in their data center in the cloud, right? And also obviously supporting network. infrastructure. So you can imagine that this one include the physical infrastructure, but it's virtualized for you, for your use, right? So as you can see, when we look at IaaS include access to network and virtualized network services. Now this is the part that um, that, that actually affects the virtualization of networking, right? Right. So there are four main cloud models. First, public cloud. Okay, cloud-based application for public clouds, cloud-based application services that is available to the general public, right? Public can access these public clouds. And then you have private clouds. Private clouds are um, more towards a specific organization or entity. Example, government could be a specific enterprise, right? Right. So that means other the public cannot access this only for certain organization. Okay, so it's private. Then you have hybrid cloud, right? So hybrid basically combine public and private. Each of them remains separate, but they are connected via single architecture. And then you have the last part, community cloud. Community cloud simply means that it's created for a specific community. Right. So, public difference between public and community clouds are the functional needs is customized for that particular community. Right. So, for healthcare organization, for example, they have special requirements due to the data they kept must be secure. Right. Must be secure up to a certain levels. Right. So, example, this one I believe in Western country the policies and law, example, HIPAA, right, uh, must ensure that this, if you provide the cloud, the cloud must be up to the laws or policies that is indicated for that particular country. That means in terms of authentication and confidentiality of those data, right? So that means this kind of clouds is provided only for the this example healthcare organization. No other um, individual or groups from not from the healthcare organization are allowed to access this kind of community clouds, right? So other community clouds, for example, I think the most popular one that you guys probably will know is the, for example, GitHub. Okay, the community here are the developer community, and it's called clouds because it's a repository. It's a storage type of clouds, repository for coding codes. Right. This is an example of another example of community clouds. Right. It's geared for a certain type of community. All right. So I've been talking about data center. Okay, and then moving on to cloud computing, right? Then I mentioned the fact that we have come full circle from data center to cloud computing, but although the names are different, data center, cloud computing, but they actually the concept is the same, right? Although in minute detail they might differ in the way they are provided to the client, right? So you can think of data center as a place where you can have equipment or infrastructure for data storage and also for processing. Processing here simply means you have computing requirement lah. Computer there. It could be because data center usually is multi user shared, right? Multi processing. So you can imagine a powerful computer doing the processing, like mainframe or servers, okay, right? So, but data center typically is used to indicate this kind of computing facilities or services for the belonging to the same organization, right? Same organization, in-house You can see here is in-house IT department or list of site, right? So that means if you are an enterprise, so your organization, you want to do computing, right? So you want to build your own computing services, computing infrastructure, right? When it's done and when you're using it, such kind of facility is called data center, right? So cloud computing, in terms of the infrastructure, in terms of the technical devices or everything there, the services there, is actually the same as data center. But the difference is cloud computing is provided, okay, as a service that is paid services, yeah, to organization. Okay, so organization just simply subscribe to the use of to computing services provided by cloud computing, but they do not need to invest initially. They do not need to invest in manpower to maintain the infrastructure. They do not need to do any kind of backup solution, because usually backup of the data is usually built into the services itself. They do all sort of RAID type of storage, where you can mirror and distribute the data. So, and location of each copy of the data is like basically different remote site. So it's quite secure in the sense that your backup is not stored in one place, right? Right. So you can see here the definition: typically an off-premise service that offers on-demand access to a shared pool of configurable computing resources. Shared pool, shared by organization that subscribe to that facility, right? So these resources can be rapidly provisioned, means very easily and very quickly provided to subscriber, okay, and then release with minimal management effort. Basically there's a dashboard. If you want to subscribe, you can tick what you want and what you're willing to, or your budget allows you to do. You tick, okay, example, yeah, if I want storage, how big, right? And if I want infrastructure, I want a server. Okay, then you can specify how much RAM you need. What is the internet bandwidth? What is the internet quota? What is the storage size you want, right? If even the CPU, you can consider as single core, dual core, quad core, and so on, right? You can even choose the type of the CPU. Is it i3, i5, i7, i9, or Xeon, or whatever? It's up to you. Okay, of course, all these choices, right? As you select them, the prices will add on. All right. So the more you select, the better the computing power capability, then the more expensive it's going to be, right? But it's as simple as that. You click, and then confirm, right? Of course, you provide. They usually work this way. You provide your credit card details first, okay? Then only they allow you to choose. They have a free tier usually for you to try out. But as soon as you go beyond the free tier, they start charging you already. Yeah. So if you want to try with Amazon, you can, but make sure you stay within the free tier. Okay, very easy. You get carried away. You click, and then you end up at the end of the month, you get a very big a charge on your credit card. All right, so that's the difference between cloud computing and data center. In terms of their capability and facility and infrastructure, what they have is the same, but typically how they manage and by whom and for whom, right, is different. Okay. So data centers are physical facilities that provide compute, network, and storage needs of cloud computing services. Right? We say it's cloud service whenever the data centers is now utilized to provide services via subscription, right? So cloud service providers use these data centers to host any of the cloud services and cloud-based resource. Okay? Okay, let's have a look at virtualization. We talk about virtualization. Here you can see AWS Management Console, right? So virtualization here simply means, okay, that the platform you want to run on it, okay? In this example, the platform we're talking about is operating system. Can be any type of operating system that you need, okay? So that means in a real data center, if I say I wanted to have a Linux server, I basically literally have to install, okay, Linux server onto that server machine. Virtualization is different. Virtualization means you already have whatever it is, you already have an operating system for that machine, right? Now, depending on what operating system you want to use, you can run under some form of virtualization software. That means you can run another OS virtualized on top of the real OS. And in a more specific version, you don't even run an operating system on top of the real hardware. You run something like a hyper virtualization, right? There are two types of virtualization software. One is running as a hypervisor. Okay, that means it installed between the hardware and the operating system. Okay, so this is a more efficient way to basically apply this virtualization. We'll see more about it in the coming slides. Yeah. Right. So sometimes when we talk about cloud computing, we think about storage. It's not only storage. Cloud computing also provide platform, which is the operating system. The thing is, whenever you subscribe to a cloud computing and you say, I want this infrastructure, this machine, then the next step will be, after you choose your machine, how much RAM, what is the CPU capability, what is the storage. Next is, what do you want to install there? That means operating system. Before you can even install any application, you have to install operating system. Of course, okay, when you install operating system on the hardware itself, it's very difficult to basically provide this feature directly through internet. Yeah, because you are dealing with the boot sector and everything that that cannot be actually delivered through the network. So what happens is, in the modern time, you are installing your operating system on top of hypervisor. Hypervisor is at least the software that runs on top of the hardware, okay, and between the hardware and the operating system. It's a more lightweight virtualization software compared to like VMware or um, basically VirtualBox that you guys probably know about, right? So one example is of a hypervisor is the one that's provided by Microsoft. We'll talk about that in the coming slide. Yeah? All right. So people typically, when you think about cloud computing, because of this, you can virtualize an operating system because you can select the virtual hardware and you say you want to install the OS on the virtual software. So that's virtualization. So that means cloud computing is virtualization. Okay, so that's how people usually think about it. However, actually, when you think about virtualization, virtualization is what makes cloud computing possible. Without virtualization, you cannot have a platform. Remember the three just now: software as a platform, software as a service, platform as a service, and then infrastructure as a service, right? The real reason why cloud computing works is that because you don't have to deal with the hardware directly. Okay, That means the hardware is there, it's already running hypervisor. You want to install OS, you can install OS, and all this can be streamed through the network, right? Because that's how you access your cloud service through network, through internet. Okay, without virtualization, right, it's very difficult to arrange multiple servers with different capabilities and installing operating system directly onto the hardware itself. Right, virtualization is the foundation of cloud computing. You can see that when cloud computing took off is when virtualization is mature. Because without virtualization, cloud computing wouldn't work. So when I say virtualization is mature, means the software, right? This technique of virtualizing the platform on top of the hardware is actually hardware supported by most of the chip, Intel, right? Intel, okay, to make it fast enough, right, to be feasible. When I say fast enough means when you're working with the virtualized operating system and hence the virtualized application running on top of the virtualized OS, it doesn't lag. Okay, before the maturity of virtualization, these are all done in software, and that makes it very slow, right? Okay, but once it matured, that means the technology is there and is supported by chip manufacturers like Intel. A lot of the things that needs to be done when you use virtualization is basically handled in hardware. Okay, there's a circuit basically helping out. Okay, so when this is now done in hardware, virtualization, okay, is helped by the hardware itself on the chip, right? Then it becomes fast enough, okay, fast enough that it's no longer considered very slow compared to the when you install the operating system on the hardware itself, right? So that's why virtualization is actually the foundation of cloud computing. Without virtualization, cloud computing will not be possible. So virtualization is simply, right, to provide another layer, okay? Because typically we think about a platform layer is hardware, on top of it is host OS, and then on top of OS in the application, right? So virtualization simply separate the OS from the hardware, provide another layer between them. When you provide another layer between them, then this OS now runs in its own separate memory space. Okay, therefore it stands to reason that instead of just one operating system, you can compartmentalize the operating system. Okay, that means you can now run, because they are separate, right? You can separate them, segment them in memory. You can run multiple operating system at the same time on the same hardware, right? So another beauty in this is that those operating system may not be the same operating system, right? So if you are accessing this virtualized OS from the internet, because they are separated from each other, it will feel to you as the client that you have the full use of the hardware, okay, and the full use of the machine. From your point of view, this is your OS is running on the hardware. No one else is using the hardware. This is what your view is, okay, from the point of view of cloud user. Okay, but actually there might be more than one OS running in parallel or side by side in the same hardware. Okay, so the one thing good is that if you want to reset let's say you want to shut down, reset your operating system, yes, you do it, but it's virtualized. The hardware is still running. Okay, you don't when you in the real world, if you only have one OS on top of the hardware, if you restart the operating system, your hardware also restart, right? But in virtualized environment, you restart OS, hardware does not need to restart because your OS is virtualized. Okay, basically just unload your OS and reload it again, Okay. Right. So historically, enterprise servers actually has a server OS like a Windows server or Linux server installed on very specific hardware. Okay. So all of the server's RAM, that means all its computing what like RAM, processing power, hard drive space, storage, dedicated to the service that it provides, web, email services, and so on. So the web email services are an application running on top of the OS, and OS runs on top of your hardware. All right. So typically, when a component fails, the service that's provided by the server becomes unavailable. Okay, that makes sense, right? So this is what we call single point of failure, because any failure anywhere will cause a service to be down, right? So in the prior to cloud computing, dedicated servers are usually underused. Underused means underutilized. They are there and they are idle for long periods of time until a client or user requests for the specific service they provide, right? Because you can only install an OS and one OS on it and a particular service or services on that server. So if there's no client accessing those particular service, then the server is idle, right? So we call this server sprawl. What does it mean? You can look at the site here. Okay. So you, for example, one server, you provide your provision for one hardware. So one, two, three, four, eight servers here. Each of them is provisioned with what they're supposed to do. So here is a web server. Here is email server. Here is SQL, file, DHCP, Active Directory, AAA radius, and network management server. So at any point, if the email is not receiving any email, not checking any email, then it's idle, right? And maybe the web server is overloaded, but because it's on the same server, the web server already reside on this machine, even though email server might be underutilized, it's not doing that much. Web server cannot offload its, um, task to the email server because they are not same service, right? So we call this situation server sprawl. So virtualization basically virtualize the operating system, and since the services as application runs on top of the operating system, when we do virtualization, we can actually separate them in memory. As you can see this instance. So let's say instead of having 8 servers, I have 2 servers, server 1, server 2. There are, of course, you have to provide more powerful hardware, right? Definitely, your RAM must be larger because you are, for example, in this example, you have 4 operating system virtualized. Each operating system may require at 4 to 8 gigabytes of memory, right? So you need to provision 8888, for example, 1632, right? So this one is 32. But you don't be surprised at very common that the server nowadays have 128 gigabytes of RAM, right? So then you can then, if you're thinking of running 4 operating system there, you can give as much as 16 or 32 gig for each of these virtualized operating system, right? So in this manner, right, they're all sharing the same hardware. So let's say this is Xeon server. You have at core, that's at core, right? So the at core is actually um, being shared by all these 4 virtualized operating system and their services. So from the previous one, you can see that if the web server here is running and the email server here is running at the same time, if this email server is idle, then the CPU or the hardware here is idle. But here, because we share the hardware, including the CPU, then we actually can make full use of the server, right? The email server is idle, that's fine. Web server, SQL server, file server might be fully utilized and is utilizing the CPU, right? Now, we do this also, that means virtualization, uh, usually with redundancy. Redundancy helps us to reduce or to manage single point of failure. Single point of failure in any system is very bad because that single point, if it fails, then it brings down the whole system, right? So what we want to put is redundancy. That means duplicates. So if one fails, the other one can still operate or take over, right? So you can see, notice here, hypervisor. Hypervisor is a lighter version, right, of the virtualization software like VirtualBox and VMware desktop, right? Why I said lighter? Because hypervisor is not trying to emulate an entire machine, right? The VirtualBox, for example, you take that, right? But VirtualBox is emulating the entire machine in order to fool the OS that you install inside the virtual machine. Okay, and that's very heavy, lah, right? Very heavy in terms of virtualizing the machine. Hypervisor basically is a lighter version, right? And a lot faster because instead of virtualizing hardware, it provides direct access to sometimes or through it direct access to the hardware. So you can see here, hypervisor is a program, firmware, or hardware that acts an abstraction layer on top of physical hardware, right? Usually, what we have right now with virtual boxes, you got hardware, you got OS, you got virtual box, then on top of that, Windows or Linux operating system. Okay, many layers, many more layers, therefore latency. Okay, using hypervisor, you have hardware, hypervisor, and then the OS itself directly. Okay, so the abstraction layer, which is hypervisor, is used to create virtual machines that have access to all the hardware of the physical machines, such as CPU, memory, disk control, and IC. Means it has direct access to it, right? The VirtualBox still needs to go through an operating system because VirtualBox is basically an application, right? Okay, so what are the advantages of virtualization? Okay, well, overall reduce costs because less equipment is required. Okay, less equipment. Compare this, to run this 8 services, we may need 8 servers. But here, each server can handle through virtualization 4 services, 4 operating systems. So you need two servers only. Definitely, you have to upgrade the server, but still, you need only 2 servers. That means less energy is consumed, less space is required. 2 against 8 servers, the space displacement, you can see that less space is required, right? Any other type benefits, which is easier prototyping. Prototyping simply means if you want to test your working environment, okay, you can deploy inside the hypervisor. Is easier. You can shut it down. You can create snapshot at any point of time, right? It's very easy to do backup because you create a snapshot. If there's something wrong, not only at the application level, you can also recover all the way to the operating system level. Okay, faster server provisioning means if your client wants a server, you can deploy very quickly, right? In fact, there should be a like a template server that is set up for web, right? You just make a copy of successfully running server. You just keep a copy, right? And if someone wants, you just make a copy and give that to the client, and the client just run that, and that is your virtualized. Okay, so very very fast. Rather than reinstall everything again and again, you just keep a copy of a standard template for web server, for example. Yeah, increase server uptime definitely, because um, if your because it's virtualized, right? Imagine your virtualized server here. Imagine instead of JCP server, I have a web server here also laying dormant. So another web server here. So at every point of time, I take snapshot. I copy a copy of my web server to another server, not running, but the latest copy, 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 right? Suddenly, server one down. Very quickly, I bring up the other server, okay? The other server to basically to run, okay? So very quickly, even if if a server fails, very quickly another server can take over, right? Improve disaster recovery. Well, again, just now, if I manage to make a copy and duplicate it different places, okay, I have a backup. And usually, cloud providers, data center, are not located at the same place. Okay, they are in fact even located in different countries. So if there's a disaster happen, you already have a copy of your data, some other data center, right? So disaster recovery becomes built in, becomes easier, right? And because of this virtualized, you don't have to install you can still install your old operating system, your old legacy software. A lot of companies, they do not want to change software that's already working. Okay, but the problem is latest hardware. Okay, latest hardware and latest operating system may not be supporting their legacy software anymore. So with virtualization, you can virtualize, right? You can virtualize the machine. You can virtualize any machine, which means you can also virtualize the older machines, and you can install a virtual version of the operating system where your legacy system is can run on, right? So let's say right now we have Windows 11. Windows 10 is still supported, but Windows 10 is going to be sunset soon. 11 is going to replace. But let's say your favorite business application runs only on Windows 7, and let's say it's not compatible with Windows 10 or 11. So what are you going to do, right? Uh, that means either you keep your old server, right, and now breaking down more and more and cannot get parts anymore, or you can just install the Windows 7 version virtualized in a more modern server. Since it's Windows 7 virtualized, your application can run in that virtualized OS, Windows 7. So virtualization supports legacy application and operating system, right? Okay, so think about the virtualization of the Nintendo, let's say the older Nintendo machine, right? You can still play those games virtualized, right? Virtualized on Nintendo old machine, where a Nintendo machine already sold out and no longer produced, very hard to get already, right? But you still like to play the games, right? So no problem. You run an emulator, which is a virtualization of the old Nintendo machine, and you can run the old games on those. virtualized Nintendo machine, right? So means this is support of legacy application. So legacy support is actually one of the highlights of virtualization, and this is how Microsoft is pushing their cloud services. They are going to rather than support all these obsolete Windows version, right? They know some of their enterprise users do not ready to give up on their old legacy application simply because it still work, right? So in terms of virtualization with their Azure framework, they can virtualize their old Microsoft Windows operating system, therefore can run their customers' legacy software. So this legacy support, yeah, very good. Yeah? All right, so a computer system consists of the following abstraction layers. Okay, abstraction layers is basically to simplify the view of the machine from the user point of view. So, when you say we can provide abstraction layers, we can abstract services, excuse me, operating system, firmware, and even hardware. Right? So at each of these layers of abstraction, some type of programming code is used as an interface between the layer below and the layer above. This is the mapping. The mapping. You have to map, right? The thing is, you have to translate what the application. Remember, application is the highest layer. It cannot access any of the hardware in any case, right? So it needs, whenever it needs a service, it means some kind of features of the hardware, it needs to send a request to the next level, which is usually is our operating system, right? So the operating system also sits on top of the hardware. Now looks at the request from the application. Okay, understand that, oh, you want to access a certain hardware. Then the operating system, okay, will directly interact, okay, with the hardware. But imagine between the OS and the hardware, you put another layer of software. This software is able to intercept the request from the operating system meant for the hardware. So when this software we call hypervisor intercepts the request, it can then map it to a um, different hardware, or directly reach the if you have the set of features, directly provide the service from the hardware. So that means you just place another layer between the operating system and the hardware. Okay, so if you can do that, that means if you can separate the operating system and whatever is child processors into a part of the memory, so the hypervisor can also load a different OS into a different part of the memory, therefore having ability to run multiple operating systems at the same time. The beauty of this is that the operating system doesn't even know that it's not directly talking to the hardware, that's one, or there's another operating system running at the same time in the same machine as it is. Okay, they don't know. Okay, so you can see here this example. This is typical how we actually um, use our machine. We have the hardware, firmware, operating system, and then we have the application or services. Okay, we simply place a hypervisor on top of the firmware. Therefore, the hypervisor can segment the memory, right? This segment is absolute because the OS only thinks it has access to this memory. In fact, the machine has more memory, but the OS, because it's controlled by hypervisor, is not able to see beyond. It's locked inside here. So when the OS has no capability to go beyond here, then this part of the memory can be installed with a different type of OS, right? So each of the operating system and the services on top of the OS uh, thought that they have the whole machine to themselves, just like this part, right? All right. Okay, so a type 2 hypervisor, this one, is software that creates and run virtual machine instances. This is how, this one is, I think type 1. This one is type 2, right? Type 2 is the one that includes VirtualBox, where you have hardware, OS, and then you run the hypervisor type 2, which is the like VMware or for desktop or hypervisor like the VirtualBox, right? And then you run OS, right? Right. So we call this type 2 hypervisor hosted by two hypervisor because the hypervisor is hosted by the OS. Okay. All right, so we talk about the virtualization of platforms, the OS and application, and we talk about the virtualization of hardware, right? So how about, because those computers that is virtualized, they need to connect to a network. So is it possible to virtualize the network infrastructure? So far, when we are dealing with network, we look at the hardware itself, right? So we know we are working with the real hardware. Okay, but in the cloud, imagine if I have a data center, meaning I have all these servers. These servers exist within a network, right? In the real data center. So if I have these computing resources on the cloud or in the cloud, does it include the network infrastructure? So in this section, we talk about virtual network infrastructure. Now, just now hypervisors type 2, we have the OS between hardware and hypervisor. Here, there is no OS itself. Hypervisor is the one that is controlling OS, the OS. The thing is, each of the OS here, right, usually without hypervisor can access hardware directly, right? But now, each of the OS here, Windows, Linux, or Unix, there are all three different accesses the hardware through the hypervisor. Hypervisor here can control the machine, right? Can control the machine so that, as I mentioned before, can segregate the RAM. Okay? Imagine this one. How many times you have to map the the OS requests via the hardware. So one layer to hypervisor, another layer to OS, right? That means translation between Windows or Linux or Unix to this OS done by this hypervisor. And then the OS talks to the hardware, right? So that means there's one more translation happening here, no matter what is this OS, right? But in the type 1 hypervisor, there's no translation needed. So it's fast. This one is faster, right? So you can see the hypervisor is installed directly on the server or networking hardware. Networking hardware could be switch, could be routed. Okay. All right. So this type of hypervisors, type 1 hypervisor, improves scalability, performance, and robustness. That means very robust. You can put in Windows, Linux, Unix, other types of operating system as long as those operating systems support this hardware. If it supports different hardware, then you need to have a hypervisor that support translate this hardware with another hardware, right? Right. Installing a virtual machine on a hypervisor. So type 1 hypervisor require a management console. This is to manage the hypervisor because I can shut down this one. I can reload this OS here, Unix OS, right? I can shut down. I can reload, restart. I can do a snapshot. I can use a different snapshot, the earlier snapshot, right? Through the hypervisor. So in hypervisor, usually it's just a software running without GUI. So in order to do all these services just now that I was talking about, loading, unloading, reloading, saving a snapshot of that particular OS instance, then you need to access it via you need to access the hypervisor via the management console. So you can see management software is used to manage multiple servers using the same hypervisor. You can consolidate servers and power on or off servers as required. So the servers here are the virtualized servers lah, right? You can then power on or off as required. Management console provides recovery from hardware failure. If a server component fails, the management console automatically move the VM to another server. Remember, if I have another server, maybe here beside, okay, let me just illustrate for you. So this is my first server. I got another server. Exactly the same. Just that it's not running. I mean, it's running, it's idle, it's just getting ready. I mean, it's just being ready. Okay? Okay, just a redundant. Let's say this one down. At every instance, depending on the configuration, I save this Windows OS into a network drive, right? Linux OS also, Unix OS also. When the server goes down, this one is running, right? So the copy is copied very quickly to here, then loaded. You know, just like your virtual box, rather than shut down the computer, the instance of the OS, you can just um, close, and then VirtualBox will ask you, oh, do you want to save this current session? You say yes. Next time you run it again, it will be exactly where you left off. Okay, so it's the same thing. Okay, if this server goes down and just Windows OS, Linux OS, all this running, it's a snapshot at the network drive is now loaded to this particular server, and this server continue running it. Okay, so this is what we talk about. Recovery from hardware failure is straightforward. If a server component fails, the management console automatically moves the VM to another server. So from Cisco, the offering is Cisco Unified Computing System, or UCS Manager, controls multiple servers and manage resources for thousands of VMs. Why thousands? Because this is cloud. In the cloud, your data center may be a humongous, large data center, like a football field size. Okay, and then your client must be in terms of hundreds of thousands of them. Therefore, they would have created thousands of virtual machines or VMs, right? So Cisco Unified Computing System is able to manage thousands of VMs, right? It's quite powerful, right? So some management console also allow server over allocation. Over allocation, what does it mean? It means multiple OS instances are installed, right? But their memory allocation exceeds the total amount of memory that a server has, right? Over allocation is a common practice because all four OS instances rarely require all the allocated resource at any one moment. So that means, imagine that we go back to this example here. Imagine that you already allocated equally, right? All three of these have equal shared to the RAM. But because, as mentioned before, certain service are idle, right? And so their usage of the RAM may not be fully utilized. Okay, just like a CPU. Okay, so Linux may be running up to here. Okay, maybe Windows running slightly more up to here. But the Unix one, something very heavy or processing, then it reached the maximum. Then, because hypervisor can see what's happening, hypervisor can take some of the memory here and allocate temporarily to the Unix OS and also up here. Okay, allocate to Unix OS. Very flexible. Okay. All right. So let's have a look at network virtualization. So to think about network virtualization, we go back to see just now our explanation about server virtualization. So server virtualization basically hides the server resources and only expose those resources that the client wants. Maybe the server has 128 gigabytes of RAM. Okay, but since the user select, well, they just want to run a very simple server, maybe just select 4 gig. So what the user see is actual 4 gig from the server. So you know this when you're playing with the virtual box, right? When you're playing with the virtual box, you can specify how much RAM virtual box is going to give for the OS that you install. And the OS will only see that much of RAM, even though actually the real hardware has much more RAM. So server virtualization hides server resources. Okay, but for network virtualization, this actually can create problems, right? When you hide the server resources for network virtualization, this can create problems, right? Think about network virtualization as to virtualize a network, right? That means virtualize all the physical network into software. We already know that some of the network capability is actually virtualized, but it's not full virtualization. So virtualization of network means virtual machines are movable, right? You think about it, server as one hardware goes down, okay, the hypervisor can move the server to a different um, hardware and continue running from there. This is actually something good, right? So we know that virtual machines are movable. Okay. Now think about it in network virtualization. If virtual machines are movable, means to say the network administrator must be able to also do the same thing. The network resource can be added, dropped, and changed, right, to support the ability of the virtual machine to move, right? So this process will be manual and time consuming if you're having a traditional network switch. Because if it's not virtualized, you go to network switch, you have to, you say you infrastructure a service. If your infrastructure is server, that's fine. But if infrastructure includes network services, then as you change your in the dashboard, right? Then if you don't virtualize network, then physically you have to go and change the setting in your switches and routers and things like that, right? Traffic also will flow differently compared between traditional client server model. Okay, so typically there is a considerable amount of traffic being exchanged between virtual servers. For example, east-west traffic. that changes in location and intensity over time. Right? North-south traffic is typically traffic destined for offsite locations, such as another data center or cloud providers or the internet. So you can see here, right? North-south traffic, east-west traffic. So you can see the east-west traffic is basically between the servers, so there will be more traffic, yeah, compared to north-south traffic. North-south here indicates going through the hierarchical layer. Remember the Cisco hierarchical layer, layer by layer, right? Going from the servers that we can consider as the what the bottom of the layer, okay? And then going up to the switch, multi-layer switch, routers, and then to the internet. Okay, so if the data movement is going through the layers, then that's north-south traffic. If we're going vertical, sorry, no, horizontal, within each layer, its own layer, that is it's called or termed as east-west traffic, right? So if a traffic is ever changing, that means it's dynamic, right? Then it requires a flexible approach to your network resource management. Okay, existing network infrastructure can respond to changing requirements. Okay, by using quality of service, right, and also security level configuration for individual flows of data. Okay, but in large enterprises using multi-vendor equipment, every time a new virtual machine is enabled, the necessary reconfiguration can be very time consuming. Simply means if you don't virtualize a network, right, or if you do want to virtualize a network, but your network is still based on the hardware-based network that we are learning right now, okay, whenever we do the infrastructure as a service, right? We virtualize the server, but we also want to virtualize the connection between the server, right? Now, every time as a client, I change that, right? I go to the dashboard, I change here, the thing is, if you think about it, let's say this is the infrastructure, right? As I change the server and how it connects to each other and so on, the infrastructure, network infrastructure supporting that also needs maybe to change, right? And if this, how do we virtualize this? This is hardware, network hardware. So that means in order to virtualize it, we need to change change the setting to accommodate the change in the virtual machines, the things that the user changes in the dashboard, right? In the cloud computing dashboard, right? We allow them to change the server. Okay, no problem. That's easy, easier, lah, right? You tick, tick, tick. Then, how about we ask them in terms of infrastructure? We allow them to change the network also. Changing the network means we have to go in here to change, right? This is what the difficulty is, complexity is. See, reconfiguration can be very time consuming because it's not virtualized as it's not virtualized as in uh, how we wish, right? We can virtualize it like in Packet Tracer, right? We can drag and drop, but that's not how it works at the moment. We actually physically have those network configuration, physical network configuration, right? But if we are able to, right, virtualize our network infrastructure, then network functions can be virtualized, right? Network device can be segmented into multiple virtual devices, which can operate as independent devices, right? We already know that there's some virtualization that is happening inside our network device already, such as the use of sub interfaces, virtual interface, VLANs, routing tables can be virtualized as well, right? And then virtualized routing is called virtual routing and forwarding, VRF. Okay. That leads us to the next section, something that is called software-defined networking. Right, before we proceed, uh, oh, Ferris joined us already, huh? Hello, Ferris. Any questions so far on virtualization? Kelvin, Noel, and Ferris?
No.
No question.
No question, Ferris? Okay. How you, Kelvin, Noel?
No.
No.
No, huh? Okay. Noel also no. Didn't hear your reply. Okay. Right, Noel?
Yeah.
Okay.
Okay.
Also, oh, Noel also is here. So I thought only Kelvin. Noel also here, huh? All right. Are you going to be in also tomorrow, Kelvin and
Uh,
Noel?
yeah. Tomorrow I go campus.
I go.
Okay. How about you, Farah? Any
Um,
transport tomorrow? Come over to campus?
yeah, no transport for tomorrow.
No transport, ah? Yeah. Or else you can have a look at our what our machines there, our Cisco hardware. Yeah. And then who knows, maybe like, can try it out. But see lah, Farah, if you can come, it's good also. But make sure, Farah, you know where are the exam hall, okay? So that because if you got your first exam is on 9 o'clock, you might be rushing, right? Rushing, and at least you know your way around. At least one time you come, know your way around the campus. So during exam, the time you're not too, too kanchong lah to look for all the places, right? Maybe you arrange that, Farah, sometime during this week. Have a look around, lah. Okay. If not
Oh,
tomorrow,
okay.
then some other day also can, lah, Farah. As long as you check out where's the exam room, check out where's whatever, lah. All right. Okay, so our next topic in this chapter is this software-defined networking. So this one, I want to show you guys the video, but I'm not sure how good is the video running. I test first. Okay, software-defined networking. Let me try. Let me know if you can hear the sound, if I play it.
Network programming is used to scripting, data modeling, and markup languages, as well as architectures and APIs, or application programming interfaces. Protocols like the OpenFlow protocol, which allows a programming language to control the forwarding plane of a switch or a router, as well as netconf and restconf. Programming languages like C, C++, and Java, scripting languages like Python, Ruby, and Lua, data modeling languages like Yang, markup languages XML, and architectures and APIs like the REST architecture and API used over a web browser, and the Java API with all of its libraries and pre-written classes and blocks of code. SDN, or software-defined networking, is an approach to networking where the network is software programmable remotely.
Ooh, sorry about that. I think our internet here at the office is not very good for streaming. Oh, mute the mic.
from the forwarding plane in switches and routers. Also listed here is OpenStack, which is a software platform for cloud computing and providing IaaS, or infrastructure as a service, which means the ability to manage pools of processing power, virtualized servers, and network storage on an as of those devices. In an SDN, or software-defined networking architecture, notice how the control plane has been separated from the data plane, and now the three devices, let's say there are three switches, could be controlled from a single control plane or from a single controller using the OpenFlow protocol. This way, the three switches can be programmed from a single point or a single software program. In this image, you can see this example further. In this case, the kit, and the software has been written in, let's say, the C or Java or Python programming languages, and the application can program the data plane on the three switches, device 1, device 2, device 3, using the OpenFlow standard. Network controllers are SDN control plane devices, which are a programmable point of automation to manage, configure, monitor, and troubleshoot virtual and physical network infrastructures. This automates the configuration of the network infrastructure. A network controller is a hardware device which locates the SDN control plane. An example of a network controller used in SDN, or software-defined networking, might be the Open Daylight platform. The Open Daylight platform is an open source SDN controller platform. You can see in this example where the SDN controller works with an application to then control the network devices, here listed as device 1, 2, and 3 at the data plane. The Cisco ACI, or Application-Centric Infrastructure, is Cisco's approach to software-defined networking and network controllers. It involves three main things: an ANP, or Application Network Policy, an APIC, Application Policy Infrastructure Controller, in this case the APEC EM, which is the enterprise module for APIC, and switches that are application programmable, like the Nexus 9000 series switches. In this example, we can see how the Cisco APEC EM works. The APEC EM, or enterprise module, is the SDN controller which sits between the application and policy and the data plane devices, device 1, 2, and 3.
All right, so that was a video about SDN, software defined network. So it's a way for us to, you know, automate and also make it programmable, right? A device. So what device are we talking about? Well, all the devices that we so far learned to use iOS commands, right? To configure, like switch, routers, so far, right? Multi-layer switch, right? Um, all these devices. Okay, if we want to configure them, what do? We have to go into that, whether remotely or using console cable. We need to go into that device, and then on that device, we perform the configuration. Unfortunately, all the devices right now are using this method. So what is this control plane and data plane? plane, it's not airplane, yeah. It's just a way to mention. It's just a word to describe all the features, the functionality, right? So basically, the data plane is the the networking data that remember when you configure and then you have to say save running config, right? Right? All those data that is saved, those are the data that actually tells the device how to operate. You guys have been doing the iOS command, right? In order to configure that device. And then you say save that configuration data, save running config, right? Remember? So that commands that configures that device is the control plane, right? Is the control plane. So the running config data is the data plane of that device. So right now it's not separate. It's very tightly stick together, right? Because your control is you type your command, and the result of the command are the configuration data, and that is the data plane, right? So in order to manage the network, you have to go to every single device and perform the configuration. And the configuration, of course, may not be all the same, even though you have um, more than one switch device or more than one router device. Each of them has their own, maybe similarity in the commands to configure, right? But there are also some maybe not the same, right? So um, what we want is actually to separate, okay, to separate the data plane versus the controller. So the controller means, what if you think about it this way? What if the the device only solely do all this? You know what they're supposed to do, like router supposed to check routing table, you know, um, forwarding data, make the forwarding decision, right? And then the thing that control how they do this is actually not on the device itself. That means you think about the wireless network just now. I'll give you an analogy. You have the autonomous AP where all the configurations is in there. So each of those each of those autonomous AP work independently. Then think about the other one using wireless controller, and it's control a lot of the lightweight AP. So software-defined networking is about the separation between the data plane whereby the device, okay, based on the configuration, is doing its job forwarding data, right? But the control is no longer on the device itself. The control is in a central location, right? This is the idea, yeah. Software defined, right? So the management plane is different from the data and the controller plane. Yeah, management plane is responsible to manage the device um, remotely, right? So you can still use the same tools like secure shell, TFTP, secure FTP, secure hypertext, HTTPS, right? To access the management plane and configure the device. Okay. Management plane is basically how you access the device and configure it, right? Right. So two major network architectures to develop network virtualization is software-defined networking. This one is the open one, yeah. Then the Cisco application-centric infrastructure or ACI. Okay. And the components, that means a mix-up SDN. You can have open flow. This one basically manage the traffic between routers, switches, wireless access point, and controller, right? So this is the basic element allowing data to flow within our SDN implementation, right? Then we have OpenStack. This is the virtualization and orchestration platform designed to build scalable cloud environments. And this is the one that provides this IaaS. Remember, IaaS is the infrastructure provision, okay, in the cloud computing. So this is an attempt to virtualize the network rather than just the servers. Okay, so infrastructure include networking infrastructure, right? So OpenStack handles this part, the networking virtualization for IaaS, okay? Infrastructure as a service, right? So OpenStack is often used with Cisco ACI, right? So orchestration here means process of automating the provisioning of network components. Okay, network components means server, storage, switches, routers, and application. So what do we mean? Just like for the server, we can provision how many servers you want, the RAM, the storage, the CPU, how many cores, CPU, all this provisioning the hardware, the infrastructure. But what about networks? When I tick, all right, I want servers, tick. Inside the servers, okay, I already tick what I want for that particular server, right? And then I want switch. I want one switch. I want two routers, or maybe two switches, one router, and so on. So the fact of provisioning is to provide, okay, to provide for the customer, okay, right? So that means customer needs those networking because devices because they want to create, okay, a virtualized network, right? You can think of basically like what you're doing in Packet Tracer. You can drag and drop, you can create your network, but imagine when you create that network, it actually is reflected by real hardware. Okay, if you drag in two switches, okay, those two switches, you selected is actually represented by in the real world. You have two switches. Okay, that is provisioned to you. Your other customers will not use that switch. But also think about this way. Those two switches operation might be virtualized. Okay, virtualized also because hardware can be virtualized as well. Right? Okay, and then think about other components. Other components include interface to the routing system, transparent interconnection of loads of link, or otherwise named as TRIL, Cisco Fabric Path, FP, and IEEE at 02.1 AQ, shortest path bridging. Right. So these two diagrams differentiate between traditional architecture and the one that we are talking about, SDN architecture. Can you see the difference? In the traditional architecture, you can see that, let me highlight here. Let's take this device one. It could be a switch. We know that the data plane whereby the capability of that switch in forwarding data is there on the switch itself. We also know the controlling plane, the software that controls the forwarding logic is also on that device, right? So if we want to configure or we want to change the control plane, okay, we have to enter that device and manage it on that device itself. Yeah. So imagine if you have in an enterprise 1,000, no, not 1,000. Let's say 50 lah, 50. 50, I think is cheap enough. Enterprise can like afford it. But as an example, I can make you feel like it's so troublesome, right? You have to go to 50 switches and configure 50 switches individually. This is the reality. So basically, here we got three. So configure here, configure here, right? So the thing is, this situation where 3 devices are basically what you do in your practical. Is it correct? Correct, Noel, Sarah, and Kelvin?
Yeah.
3, right? That's what you do. Yeah. Imagine in enterprise you have 50 switches. How you feel? How you feel, Farah? Kelvin, you say suddenly your boss say, "Can you go and configure 50 switches?"
Too much.
I think for the rest of the week you'll be very busy. Just too many, right? But that's how it is right now. That is how exactly it is. Imagine, yeah lah, because you guys are still learning about it. That's why configuring a few switches also it takes a while, right? But even if you're already expert, okay, configuring 50 switch, you still do need some time. I'm just talking about 50 switch. If you go into a proper enterprise switching room, where you put all the router switches, you can see. I go to the telecom. I ever went into a telecom. Just one. I think one room only, not other rooms. From floor to the ceiling, you can see all the switches and routers and what else, right? So imagine you have to configure that. I think you need teams of people to do that. And then look at the other side. On the right-hand side is the SDN architecture. Okay, the one that the trend, we are moving towards this kind of architecture. The separation between the control plane, and we call it the SDN controller, with the data plane. So instead of configuring each one, we just go to a central controller and control it. The dream, or my dream, is that I can have something like the packet tracer, but we can automate it. Remember I said about automation, that not automation precisely, but you guys can type the commands into a text box, right? And then once you type the commands there, what if a program generates that command? Kelvin, Noel, and Farah, what if I can write a program, and inside the program is configuration, right? I can just put in what I want inside the program. The program just I use the program to maybe ask me a few questions about the configuration. I type, I fill in the blanks, whatever form, whatever. I don't have to type all these commands. Why should you? Why should I? Think about it. And I click generate, or I don't even have to click generate. But let's say no SDN yet. Let's say I have a program, I wrote a program that can generate iOS commands based on configuration that I want for the switch or for the router. This program understands what I want and then generate the command. I just simply copy, paste into the switch or router, and it's settled. Wow, that kind of software, if you guys have it during practical tests, would be nice, right? Calvin, Noel, and Farah?
Yeah.
Oh, yeah.
Yeah? Okay, beside the point, do you think you can write such kind of program?
No.
Possible, right? Possible, is it? Commands already there, just put the interface there. Isn't it? Oh, can.
Oh,
But
okay.
now think about it this way. Think that there's a dashboard, and you can actually, it's an interface, something like the packet tracer. And then you say, using humanized, I can write the program, right? To set the configuration as I want based on my requirement. I just simply say my requirement, or write down or fill in the form for my requirement for switch, for a router. For this particular router, this particular switch, what I want. Imagine in cloud computing, I provision one switch, and there's a form asking, for this switch, what do you want? Oh, this switch, I want this. In terms of security, this part, I tick. This is basically the provisioning currently for hardware inside cloud computing. So let's imagine we do it for SDN. So that means here I can set what I want this device to do, what I want this device to do, what I want this device to do. Then I click submit, generate or whatever. Then this device is then programmed to do what I want. I don't have to go to each individual device. I can set it from a controller. That controller can be a server, can be a computer, can be a software running, right? Okay. To enable this, you might use OpenFlow, right? OpenFlow to connect them. So this is basically software-defined architecture, because the architecture of your network is defined by software. We talk about the switch, right? We can also talk about the routers. You can also do the same for routers, right? So you can see the definition here. The SDN controller is a logical entity. So it's actually program, right? Just now I talk about program. So that's why it's logical entity. Whenever it says logical, it's usually meant it's implemented in software. Okay, it says enables network administrator to manage and dictate how the data plane of switches and routers should handle network traffic. And that is exactly what you do with iOS, isn't it? You go inside the switch and routers and then you type your command. So why do you need to do that? If I can do it from an SDN controller, and SDN controller contact the switches, routers, and relay the configuration, right? So this SDN controller can orchestrate, mediate, facilitate communications between application and network elements. So application, basically a business application, SDN application, and the orchestration in the cloud simply means I have a dashboard. I can click. Okay, after I click submit. Of course, there are programs behind it, translate what I want via my clicking, filling up the form into programs that are going to connect to the control plane, and then depend on whether it's going to be routing, traffic engineering, mobility, whatever, that's a controller. It goes to the actual data plane. It goes to the actual hardware and implement it. Okay. So how do we connect to this SDN controller? Well, via API. API, as you know, is application programming interfaces, right? It's a way for us to access the whatever functionality, right, that is provided inside our program. So basically, you include that API library, then you use the features, the function, right? Function or methods or class, whatever, okay, as provided as part of the API. Then you can then use it in your program. So that means it's programmed, that means it's programmable, then anyone can write the program based on the API. So my implementation, maybe I still love to use command line. So my implementation maybe is still command line interface. Typing that to configure, and then it goes via API. But who wants that anymore, right? Maybe mine is to use a drag and drop interface, GUI interface. Or even better, I'm a very visual person. I use a virtual reality headset. I create a virtual reality configuration. I can then grab here, grab there in my virtual environment to configure. It doesn't matter because it's using API. As long as how my GUI right, represent itself to connect via the API to the services or features or functionality in the control plane, it will still deliver that configuration onto the routers and switches at the data plane. Right? So this is basically the dream of this SDN architecture. Right. So talk more about the controllers and operation. Oh, by the way, guys, I know I'm already into nearly 3 o'clock. So we continue until 3 o'clock, and then we take a break. But I do wish to finish up our chapters today. So I think I just prepared you the question first. Later we can discuss about the answers for the tutorial. But I think the next hours I will continue with to finish up the final chapter. Right? There's a bit of a lot of topics as you notice for this chapter 13. Okay, last week we talked about the network management, right? Let me just check very quickly. I believe it was a couple of a big topic actually, network virtualization, network automation. Yeah. So also network virtualization, I think it's not mentioned here. Hang on, yeah. I think where is it? This one. Yes, actually, last week was network design and network troubleshooting, the two very big topic there. And this week also same chapter, virtualization and automation. So after virtualization, we're still going to look at automation, right? Automation to automate it, right? So let me just check this part. Right, so this is the last topic. It's about 1, 2, 3, 4, 5, 6, 7, 8, 11 slides here. All right, so I think after this 11 slides, let me take a break before we move to the final top, section, which is automation. Is that okay, everyone? Is that okay with you? Yeah, too many, right, Farah? I don't know why they reserve towards the last semester. They put 2 topics per chapter, and this chapter is chapter 11. 4 topics, main topics inside it. Right? Fully. I think what they did was they put all the theory there, so you don't have to do the practical. I believe so. But we'll try to finish this part, this controller part, and then we'll take a break before doing the last topic. Okay. Right. Okay. So let's. Oh, okay. Yeah, controller. All right. So we talked about the controller earlier on. I talked about the because using API, the capability for the programmer, right? So I think in the future, so later, network engineer can also be a programmer because you need to write programs, right? At the controller side, this one, SDN controller. Okay, this SDN controller, that means there's API. That means whenever you have API, means your program will access those API to access the feature. That means programmer is needed to write the program to access the API, no matter what. Whether you write the program or you write a program that is where you run the program, it does that, or the program is actually part of the GUI for you to be able to do a more intuitive configuration, right? Still both need programmer. Okay. Previously, it's just like you as a network administrator, you go into the device and you do, you do your own configuration. You type all the commands, right? You have to memorize these commands and so on. You type in, right? But now you can program. Okay. Right, so SDN controller defines data flow between the centralized control panel or control plane, sorry, plane and the data planes on individual routers and switch. So you can see the open flow switches here, SDN controller here, and then the software secure channel. Right. So you can see each flow traveling through the network must get permission from the SDN controller, which verifies that communication is permissible according to network policy. So SDN controller using open flow protocol over TLS, which is very secure, right? Go to secure channel to ask for permission, right? Okay, and then complex functions are performed by the controller. The controller populates the flow table. Switches manage the flow table. All right. So that means the decision is no longer on the switch. Decision is provided by the SDN controller. If you recall, switches make forwarding decision every time, right? Because you configure it to be so, right? But the switch still need to do forwarding decision. But here, what if the SDN controller is the one that is based on policy doing the decision, and then the result of that, the rules of the decision is now stored in the flow table inside the open flow switch, and the switch simply don't have to do any decision making. The switch only follows the flow table. You know, if it gets that means you offload the decision making process to the controller instead of the switch, right? All complex functions are performed by controller. The controller populates flow table. Switch manage the flow table. So you can see there, right? Now inside the switch, okay, inside each of the switch, a series of table which is implemented in hardware or firmware are used to manage the flow of packets through the switch. Okay, so the switch, what the switch see is a flow is a sequence of packets that match a specific entry in the flow table. So the arrangement of this entry in the flow table is done by the controller. The switch doesn't do anything, have anything to do with the flow table. The switch only look at the flow table in order to manage the flow of the packets. Right. So the three table types that we see before was flow table. This is table match incoming packets to a particular flow and specify the functions that's to be performed on those packets. Right? So there may be multiple flow table operating in pipeline fashion. Then you have a group table. This group table um, trigger a variety of action that affect one or more flows. And then meter table, this one triggers a variety of performance-related actions on the flow, including ability to rate limit the traffic. Right? So these are basically groupings of
Also DC kah?
very few organizations actually have desire or skill to program the network using SDN tools. That's because, hang on, yes. Hang on. network okay kah? So the network okay kah? Right. Disconnection seems like unstable. The connection. Right. See lah, like later, see whether I think should be still okay. Okay now, okay? Yeah. So the I think the reason why, yeah. Thank you, Farah. Yeah, you guys can see this one, right? It says not many organization have the desire or skill to program. Okay. Um, Desires normally because things already working well for them the way it works, right? So a lot of especially organization enterprise they are very slow moving. I can tell you because uh, um, they simply would not change the way their you know, organization work simply because there's cannot hear properly. Yeah. Okay. Resume in. Hello, everyone. Noel, not coming. Okay. That's fine. So only Kelvin lah. Kelvin coming.
Yeah.
Kelvin coming. Okay, okay. So okay, tomorrow we'll be at the what lah? Huh? Cisco lab. All right. Hang on. Yeah, can lah, Cisco lab. Computer can be used. Okay, I'm not sure whether they fixed the projector, but it's okay. You can use the computer, right? And I will conduct from the what? From the lab. All right. So welcome back. So we are looking at Cisco ACI. I think it's you can see that it's a Cisco implementation of SDN, right? So you can see that here it says that Cisco developed the application-centric infrastructure, that is ACI, to meet objective of SDN, but they improve on it. So it says here they got more advanced and innovative ways compared to the earlier SDN approaches. Right, so ACI is implemented in hardware. It's a hardware solution to integrate cloud computing and data center management. Right, so at a higher level, the policy element of the network is separated from the data plane. Again, very similar to SDN. Yeah, SDN also separates the control plane and the data plane. All right, so it's basically this separation simplify how data center networks are created and managed. Right. Right. So for the ACI architecture, we can see there are three core components. Right. The application network profile called ANP. Right. So ANP is actually a collection of endpoint groups, including their connections and the policies that define their connections. Right. The second component is the application policy infrastructure controller, or APIC. Right. So it's a centralized software controller that manages and operates a scalable ACI clustered fabric. Okay. It's designed to be programmable with centralized management. It actually translates those application policies into network programming. So basically implements the policies. Right? Usually policies are a set of rules or procedures from the organization, right? These policies define your network policies, right? At one example, like if you recall the ACLs, right? The access control list, those are policies. Policies governing what traffic allowed or disallowed into certain part of the network, right? So these are policies. Okay, so how we do it right now is just we enter it directly into the router. Okay, so let's say we have other or similar policies. There is policies that is created or following the organization's procedures, right? So these policies, in order to be implemented, would be translated into network programming. So whatever language you use, right? So now we saw that Java is used, maybe used, or Python may be used. Whatever language that you program into, it will implement these policies, right? And then the third components you can see here is the Cisco Nexus 9000 series switches. So if you recall, in the last week, we looked at several of Cisco's, Cisco brand devices, including switches and routers. And I think one of them is Cisco Nexus, right? So this particular model, Cisco Nexus 9000, provide application-aware switching fabric and work with the APIC to manage virtual and physical network infrastructure. So that means it actually can work with without the virtual with physical, or together, virtual and both physical, right? So in these three components, the APIC is positioned between APN and the ACI enabled network infrastructure, right? So the APIC application policy infrastructure controller, yeah, translates the application requirements into a network configuration to meet those needs, right? So what it means, basically, you have a way to specify what is your policies, right? And these policies are converted into a sort of application requirements, okay? And it's then implemented using programming, yeah, network programming. And this network programming will then be used to apply this network configuration. You can see that, yeah. So basically, it's simplifying, management of this network devices and its connectivity, yeah, means the whole network infrastructure. Right. So you can see what are the samples of application network profile, right? So there's few examples here, right? Customer or tenant, and then contract simply means what they want the network is used for, right? So if I'm a client, I can tick, tick, tick. I want this, I want this, I want this. These are the policies. This is a contract, right? It's between the customer, right, or the tenant. That means the subscriber to the cloud infrastructure, right? So what I want is translated into a contract, right? This is one profile. Then VLANs is another profile. VMware as the virtualization, okay, software, okay, and then web services. Web services could be like a web server providing web pages and so on, and then application and database. These are all different set of network profile because the requirements might be differing from each other. Okay, so they sit on top of the epic, right? The epic is the one that's going to provision the implementation of all these policies, from this profile into translate it into the configuration that you have to implement onto the network itself, right? Okay, so let's talk about Cisco ACI Fabric. It's composed of EPIC, right? EPIC and the Cisco Nexus 9000 series switches. So these are the physical switches that's going to implement the architecture of the EPIC, right? So you can see that the example here is using two-tier spine leaf topology, as shown in the figure. The leaf switches attach to the spines, but they never attach to each other. So you can see an example, right? In here, they are attached to the next layer, right? But they're not attached to each other. Can you see that? Right? So indirectly they're attached to each other, but they're not directly attached to each other. Right? Now you can see the same situation at this layer. Right? The switches connect to the next layer above and the next layer below, but never to each other. Same as the network devices. Right? So this is called as this is called as a spine leaf topology. Right? So when compared to SDN, well, we compare because this EPIC is Cisco's ACI, sorry, is an implementation by Cisco following SDN, right? So the difference between SDN is that the EPIC controller does not manipulate the data path directly. Okay. Instead, there's another layer called policy definition, which is centralized by the EPIC, and it programs the leaf switches to forward traffic based on defined policies. Right? So basically, if you have like a set of policies, it's translated into network programs, and the programs basically contact the switch to set the configuration. It's programmable, right? So then the switch will use that, okay, to as a way to know how to forward traffic, Okay, so policy, and then the program. Okay, program implement those policy onto the switches, and the switches just follow, right? Follow the configuration. Right. Next, we look at SDN types. Right. So we have Cisco Application Policy Infrastructure Controller, the EPIC, right? Enterprise Module or EM. It extends ACI that aims this implementation on the enterprise environment. Example also will be campus deployment. Okay. Right. So let's have a look at 3 types of SDN, right? That can give us an idea of what is EPIC EM or enterprise module. Right. The first one is device-based SDN. Devices are programmable. So we've seen this earlier on. We have application, the controller, controlling the device. The device basically just handles the data plan. Okay, the data plan means the forwarding of messages of data. Okay, so devices, these devices here, down here, are programmable by application running on the device itself or on the server in the network. Okay, right. So controller-based SDN. So the controller is separated. There's an application running on top of SDN controller. So in this model, we use a centralized controller that has knowledge of all the devices in the network. The application can interface with the SDN controller. So basically here you got APIs, right? APIs, the SDN controller API application accesses this controller, whatever the controller features are via the API. Okay, you can see that the application interfaces with the controller that manage the devices and manipulate traffic flows through the network. Okay, so Cisco Open SDN controller is a commercial distribution of a protocol called Open Daylight. Okay, and then the third one is a policy-based SDN. So it gets a little bit more complex. We just put in between the application SDN controller a set of policy. Thereby, the policy defines what the application or the program can ask the SDN controller to do. Okay, so here the simplest one is here, right? Application directly accessing the device data plane, right? And then here, application, access the controller via APIs, and the controller controls the data plane. Here, the controller might be at the device also, together with the data plane. Here we insert a policy in the middle between application and SDN controller, so that the organization policy will be involved, okay, in the access of the controller from the application, right? So this you can see here, it says if guided workflow and user-friendly GUI is provided as part of the application, then no programmings are required. Okay, so Cisco EPIC EM is an example of this type of SDN where we have the policy. So basically, we can embed the policy with application. Application basically is a GUI based program. So it means, in actual fact, you can imagine a dashboard, a configuration dashboard. You can tick, enter certain things, select certain policies, select to implement certain policies, right? And then when you click apply, something like that, it sends a command to the SDN controller. Controller then controls the switches or devices, including routers, perhaps, right? Right, so Cisco EPIC EM provides single interface for network management, including discovering, accessing device and host inventory, viewing the topology as shown in the figure. So this is what I was talking about earlier on, the interface or the dashboard looking like the packet tracer. So you can see here, we can actually see an icon representing the devices and lines representing connectivity here. Right, so But this representation here actually have a representation in the real world, because you can see here it says discovering and accessing device and host inventory. Meaning to say, if you click on a certain device and you you want to control that device, right? Then you are actually controlling the real device in the real world. Okay, this is a digital twin. This is a representation of the real hardware. Okay, so you can see this is a topology, right? A real topology. You can also see the connectivity between them. Which is, you can set the policies for each of them, and setting policies basically is a set of configuration that you can do on these devices, right? And then we have the Epic EM path trace tools allows the administrator to easily visualize traffic flows and discover if there is any conflict, duplicate, or shadowed ACL entries. So basically, the configuration that you make, I can tell you the way I see it. This is the next natural flow from having the packet tracer used as a learning tool, where the same interface can be used as a dashboard to control real hardware devices. So basically, you can see here we've done some ACL entries before in our exercise. Remind you that ACL represents access control list, right? So here we can, even as a network administrator, I can even see if there's any conflict affecting the flow, the traffic flow in my network, right? Let's say I have a misconfiguration of ACL, and this is causing conflicts, blocking certain traffic, and there are duplicate entries, right? Then I can see it in this dashboard, right? So this tool can examine specific ACLs on the path between two end nodes, right? Displaying any potential issues. You can see where any ACLs on the path either permitted or denied the traffic, okay, as shown in the figure, right? Notice how branch router 2 is permit all traffic. Let me see, branch router 2 permits all traffic. I can't really see here. It's not very clear for mine. Hopefully yours is more is clearer. Okay, it's your slide, right? The network administrator can now make adjustment if necessary to better filter traffic. So it's a more intuitive and user-friendly way to implement policies, or the access control. Basically are the policies, organization policies regarding network traffic. So it's a better way for you to do that, because you can actually see what happens if you place or incorrectly place ACL, right? What happened to the network? Okay, rather than physically you connect to the device, enter the ACL, there's no way for you to know, and you have to do troubleshooting like ping, 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 just to find out. Right here, these icons here can represent your real network devices and the real outcome of what's happening when you're doing certain configuration. Example here is ACL. Right, so that's the end of our this section, yeah. Right, so the lab actually is virtualization, installing Linux and exploring the GUI. This is a lab on virtualization. I'm not sure. I don't think this one we do this one, but you guys have done operating system before? Any of you done OS class? Which machine Kelvin already done? VirtualBox. Excuse me.
VM, right?
You use VirtualBox? VMware.
Yeah.
VMware also, I think, has a free edition. Yeah, VMware. So the other one is VirtualBox. Whichever you want to use. They're both very similar. So VMware, Farah, ever used or not? Yeah, VMware, right? Allows you to install OS on top of OS. Yeah. So you install VMware Desktop. I think it's Desktop Edition, and VMware Desktop Edition, and then let me just see article, not article. This one. Think I can't see the one that's free version. Not sure got free version. Still got free version, Calvin? Oh, you used VMware before. All right. So the other one is this one. This one is more open from Oracle VirtualBox. Or you can use the built-in Windows version as long as you have Windows Pro. So you can use the Windows version, right? VirtualBox or VMware. I'm not sure. Last time I used to use VMware, but I think because they start to, do they still provide the free version? I'm not sure. Yeah, can't tell which one is the free version. Yeah. So it's a good way to learn about OS now without installing operating your current OS. I think it's Microsoft. What's it called? Hyper. Yeah, it's called Microsoft Hyper-V. It runs as a hypervisor. Is it? And then runs a hypervisor, and then Windows runs on top of Hyper-V, the hypervisor. See, you can see. Okay, it's available for Windows Pro, Windows 10 Pro, and as long as you are Pro, you can have hypervisor. And then the other open source hypervisor is called Zen, I think. So this one's open source, right? So you install on top of your hardware Zen, right? And then run and then you can install Windows on top of it, and then Linux on top of it, and so on, right? So you can have multiple. And so the Zen, actually there's a management console, so you can switch between Windows, and Linux at any time, right? You can do it if you don't think you want to play games, right? I think games still suffer under virtualization. But in any case, it supports it supports Linux and Windows, right? Okay, so you might want to try later after exam. just because I scared your computer get if you're trying out this hypervisor, and suddenly your computer doesn't work. You need time to work on it. So better do after exam if you want to try. Or you have another computer that you don't mind if it's I don't think it's gonna damage your computer, but if you misconfigure, maybe you have to reinstall. Anyway, you install Zen first, then you install the OS on top. So that's how Type 1 hypervisor work. So these are some examples. The VMware, I'm pretty sure there's a version for Type 1 hypervisor for VMware, but VirtualBox is Type 2, right? All right, so I think that's it for this one. Windows is more used compared Linux because one thing is because the Windows supports more game. Why I say that? Because gaming industry, of course, it includes console and Windows gaming. Is actually the largest at the moment is a large industry, larger than Hollywood, and a lot of people play games. Even though console is selling well, there's still a lot of people play games on Windows, right? So I'm talking about the normal users lah, not yet the. I'm not talking about the enterprise yet. So a lot of people, if they want to play the specific games that is supported, usually nowadays it's getting better, but most of the games basically runs under Windows. Okay, very few they are, but very few runs under Linux. So you can do emulation, but emulation slows down the game, right? So with the DirectX, we don't have the DirectX drivers for Linux, so that's why you cannot easily port over to Linux. You have to use OpenGL, and I think a lot of developers don't have the manpower or time to port over to Linux. So in terms of that, that is why Linux is not more in home use, but in web use as a server, there are more Linux server than Windows server, simply because Linux server is highly capable. Second, is free, right? In Windows server, it's very expensive. It's license based on user, right? So in the internet, there are more Linux server compared to Windows server, but in the consumer base, there are more Windows OS rather than Linux OS. Okay, because simply due to compatibility, software compatibility. There's more software written for Windows and than Linux. Linux usually got the majority of the open source software, but any of the proprietary one, not many, right? You have to use emulator, right? In terms of other things like enterprise, okay? So in enterprise, usually server based, yes, still Linux also wins, but in terms of workstation, okay, Windows usually selected by enterprise lah. Most Fortune 500 companies also use Windows, right? But in countries where they do not want proprietary, they want open source, so they can basically customize the OS. Then Linux is more popular. Okay, does that explain it, Farah? Does my answer explain your question, Farah? Oh, okay. Okay, good question actually. Why is Windows used more than Linux? Yeah. So if we talk about consumer, yes, because application and games, software. It is also the reason why Windows failed their Windows Phone. They cannot fight Android and Apple simply because application, right? Application in Android phone, there are so many in Google Play Store compared to Windows Mobile Store, right? Application is the key. And in Linux, there are so many games that is not compatible. It's not available, especially AAA games, and it is so crucial, okay, because gaming industry is so huge. It's bigger than Hollywood, so you can imagine, right? But in terms of server, Linux is winning. Linux is winning because server is the Linux as a server is highly capable but cheap. It's free, right? Only the maintenance. If you basically don't know how to maintain Linux server, then you hire professional. Red Hat basically do that. In fact, they're earning so much because of this. They're earning so much. That means they break even 1 billion. Because even though Linux, they don't sell Linux because Linux is free, open source. What they sell is their service and also some of the enterprise level management software. Okay, they actually include in their Linux, and they provide this service product as well as support for that. And Fortune 500 companies that prefers Linux server actually willing to pay, right? They don't pay for the Linux OS, but they pay for the support. They pay for the extra software, okay, enterprise version software, and the maintenance, the upgrades, all this provided by Red Hat. So that's how Red Hat make money, and it's actually very lucrative, right? They actually earn billions. What 1 billion? The profit went over 1 billion. I think a couple of years ago, right? First time a company based on open source can make so much money, right? And that is why Microsoft also is including Ubuntu and other distribution into Linux, into Windows, because they know developers. There are many developers that actually make use of Linux. So rather than losing them to Linux, they say, okay, you can use Windows as development platform and still work on your application within Windows, right? So you can, but for Windows 10, the best you can do is Ubuntu terminal environment. If you have Windows 11, then I think with WSL version 2, you can install Ubuntu GUI as well, the GUI part, right? So that's why Microsoft is now supporting. And then you can also, they're also planning to support Android store. Right now it's Amazon, okay? Amazon Android store, right? That means Windows 11 will be able to run via an emulator, and the emulator is quite good. It's quite fast from the testing. It's able to run Android software. That means you can sideload also. Yeah. All right. So I'm going to stop recording now. Unfortunately, we still do have one last topic, which is network automation. But never mind. I will try to fit it into tomorrow. Okay, 1 hour of it tomorrow. I think simply because tomorrow practical is basically feedback on skill-based assessment recently. So I think I can make use of this session, okay, to finish up our lecture, and I will ensure that you guys have the latest tutorial. I think I've already shared also that one, but just in case not yet, I will update it. Let me see, participation up to network design. Yeah, tutorial is already uploaded until automation. So just try to do the network design, troubleshooting, and virtualization. Okay, automation will finish up tomorrow, so you can add in for that for tomorrow. I can see here. Okay, I already put in. Okay. So some of you already start doing. Kelvin also start doing that. Okay. and Noel as well. So maybe as the end, student ID. Student ID, I'm not sure because you see, our student ID comes from KL. So I think they also come in a batch. So I'm not too sure. 10-4, 10-4. Oh, 8 days, one week already then. I don't know how long they will wait for the one batch. I can maybe ask lah. I can ask and see. Okay, I can ask for you. Right? You want the student ID? I know it's for the what man? For being inside our campus also for the exam. Okay, I will ask. So 10-4, so about a week already, yeah. But usually they put it into batch because if sending in a batch is actually more economical and also more efficient rather than one by one. Can anyway, I'll check for you. All right, so I'll see you guys tomorrow. Now it's already end of our session. All right, so I'll see Kelvin in the lab tomorrow. Yeah, Kelvin, but I will conduct it from the lab. All right, okay, Noel. Bye, Kelvin.